Hi, Mick McQuaid here to welcome you again to Database Management. This is the second of 6 introductory videos. They're all from week 1, so they all start with 01, and they're lettered A through F. I think last time I told you there were 5 of them lettered A through E, but I forgot about the 6th one. So this one is what, and it answers the question, what will you learn? Which I mentioned in the previous video. So the first thing that you'll learn is what databases are, and I'm going to tell you that databases are structured collections of data, but you have an assignment this week to tell me what databases are, and I don't want you to use this definition. I want you to think back to your preconceived definition before I told you this definition and tell me what you thought databases are. Most of the databases that you'll encounter are relational databases, particularly in the workplace. You mostly encounter relational databases. And database management systems that manage databases are ranked in terms of perceived popularity by a website called DB Engines. And it doesn't rank the actual popularity, it's the perceived popularity based on mentions on discussion boards and the like. And most of the database management systems that are listed there are listed as multimodal, but they're mainly relational, in fact. What is a relational database? Well, it consists of related tables of information, although that's not where the word relational comes from. Each table looks roughly like a spreadsheet, and each row in that spreadsheet describes a unique entity, and no duplicate rows are allowed by the relational model, the theoretical relational model that we're following. But unfortunately, most software fails to prevent duplicate rows, so we have to enforce that manually. And I'll show you how we do that later. Each column describes a property of the entity, and no duplicate column names are allowed according to the relational model, and most software does enforce that. And the columns are all named, so an unnamed column obviously would invite duplicates. Each column contains only one type of data. It can be a type of text, a type of a number, a type of a date, and so on. There are many kinds of dates, many kinds of numbers, and many kinds of text. And the rows can be in any order. They are specifically required to not be ordered according to the database software. The database software can reorder it itself without your intervention for efficiency purposes. So you can't depend on any order. And the intersection of a row and column is called a cell, just like in a spreadsheet. And there are also technical terms for all these things, like technical terms for row and column that we'll learn later. Databases are old and they've been, changed over time, and people have developed a lot of technical jargon and terminology and so on. And when I say they're old, I mean databases are really old. So here's a 5,500-year-old clay tablet, Sumerian tablet that records a transaction involving beer and hops. And this is the oldest transaction record artifact that we have today. There are many older human artifacts, but this is the first artifact that could be construed as the row of a database. And as I say, they're as old as record keeping. And relational databases were invented in the 1970s. And they quickly supplanted what was then the dominant kind of database, which was called a hierarchical database, became the dominant way to store data in organizations. And if implemented correctly, they guard against data anomalies. They're actually a very good way to store data, and they can be made to operate very quickly. For example, an airline reservation system that you use online is backed by a relational database, and it can operate moderately, for moderate levels of satisfaction. The way that people work with databases is generally through a language called structured query language, pronounced either SQL or SQL. I'll vary between the two. And it's the standard language for working with relational databases. It's one of the oldest computer languages still in use today. It was developed at about the same time that the relational model was developed. And it's idiosyncratic compared to modern languages. And I use Python as an example of a modern language. Python was actually developed back in the 1990s, although it's changed a lot to become more modern. People have invented all kinds of alternatives to SQL, but none of them have received adoption as widespread as SQL. So you're better off learning some SQL than one of the many less known alternatives. In fact, there are even new avenues for using SQL being developed in 2026. And large language models are good at SQL. In fact, they're so good at SQL that we'll talk about them in this class. And you can even use smaller large language models that can fit on a laptop, like Qwen 3.6 Coder or something like that. Oh, I'm sorry, this beeping is not related to the class. Let me turn off the beeping if I can. Anyway, how do we get data into and out of databases? So you use a database management system, which I already mentioned, to work with databases, and you can get data into a database by many methods. So you can have a graphical user interface called a GUI or a command line to do it. Usually people write programs to get data into databases, one entity at a time, or as a result of an event like a transaction. And you will, in this class, you'll probably use comma-separated values files or spreadsheets to get data into and out of databases. And work groups often use spreadsheets, but the organization as a whole uses databases, and as a result there has to be a two-way street. Ooh, this is going off the screen. There has to be a two-way street between the databases and the spreadsheets, or between the databases and the CSV files. We're going to use a particular database management system called SQLite. That's pronounced in several different ways. I usually call it SQLite or SQLite 3. And it's a database management system, and it's a serverless database management system, which makes it easy for us to work with. It is by far, and I mean by far, the most widely deployed database management system in the world. And it's free, which is an advantage, and it's very well documented and well tested too. I should have added well tested here. Here's a page from the SQLite website, the most deployed.html page, and it lists where SQLite is deployed and suggests that there are probably over 1 trillion SQLite databases in active use. However, on the DB rankings webpage, it's only listed as number 11 because it's not talked about that much, because it is an embedded database. So you don't actually know about most of the SQLite that you use. The kind that we're going to use, the command line version of SQLite, is itself not that popular compared to Oracle or MySQL or Microsoft SQL Server or PostgreSQL. These are four popular client-server database management systems. So in contrast to those are client-server. This one is embedded. It's embedded in other programs such as web browsers, mobile phones, and desktop applications. And it's a single user database management system, which is why you can embed it in other programs. It's designed to be used by one person at a time. Now, it's not always used by one person at a time. It has actually been shoehorned into multi-user situations, but it was originally designed to be one user at a time. And it's file-based, which means that it stores all the tables of a database in a single file. Client-server databases store all tables in separate files, usually. Okay, normalizations of databases. And by the way, most of what I talk about is usual. So there are all kinds of edge cases and corner cases that violate just about every rule you can name, but they're just that, edge cases and corner cases that you don't encounter very often in the world. So if you design a database without regard to a thing called anomalies, you will get anomalies. And anomalies are problems that can occur when data is stored in a database. And there are three main kinds. So there are update anomalies. So let's say that I move and my address is updated and people keep sending mail to my old address because they didn't update the address properly, or their database wasn't designed, so they have like maybe multiple records of my address, and one of them is correct and one is incorrect. There are also insertion anomalies. So for example, if I design a database poorly, I might design a database for this course, for courses that require that a student sign up before the course can exist. So the course can't exist without a student in the database management system, but the students can never find it unless the course already exists. So that creates a catch-22. And then there are deletion anomalies. So if I store my customer's information in the transaction file of a thing that they bought from me, and then they return that thing and I delete that record, then I've lost all track of that customer existing. So I have to design the database carefully so that I don't accidentally delete information that I don't intend to. So normalization is a process where we organize data in a database to reduce anomalies. And there are several what are called normal forms, with each one having specific rules that we're going to learn in this class. It's a main component of this class is to learn first, second, and third normal forms. There are some other normal forms we'll mention, but we won't really learn them. And normalization is the process of decomposing tables to eliminate redundancy and improve data integrity. So in your project for this class, you're going to develop a database, and it'll probably start out as one big table, and then you'll decompose it into many tables to eliminate redundancy and improve data integrity. And this involves splitting tables into smaller related tables and defining the relationships between them. And it ensures that each piece of data is stored in only one place, which reduces the risk of inconsistencies. So that's the end of that. And I look forward to you watching the next 4 videos in this series. Thanks for your attention.